Bonjour, merci d'être venu. Welcome. Thank you for coming. So, I mean, it's a question that has been asked to me a few times. So let me just to summarize this business of limits. So if you compute, if you are interested in a thermodynamic quantity, then the perturbation is time independent. So you're just looking at the response and you look for the system to equilibrate. So it means that you're looking at a zero frequency response function. So you take zero frequency before Q equals 0. In the case of DC conductivity, for example, you're computing transport at zero frequency. But if you think of atoms, they all have a discrete spectrum. So if we put them together and we have a DC response, it means that we're looking at an emergent phenomenon, the Fermi surface, in other words. In other words, there are states now that are extended, and these states can have arbitrarily small energy because the system is infinite or it's large. So it means that if you want to compute the DC conductivity, you have to take the wave vector Q goes to 0 limit first, just to make sure that you are in this limit where the system is infinite and you have a zero frequency response. So does that clarify things? That's another way to look at it. Okay, you have questions on this? Okay, so today I will spend a few minutes to talk about self-energy in a very phenomenological way. And then we moved already we jump a lot of chapters. I think that doing the harmonic oscillator has given us the elementary notions we need. And we go to finite temperature Green's function that we need after that to do the electron gas and everything, because we need to know how particles propagate. So to do that, I need the second quantization. So second quantization is in chapter 24 and 25. But these chapters, they treat fermions and bosons, and they go in all sorts of details. So I will follow the summary, which is at the end of the lecture notes, so chapter 81. So, but you will see it's very easy. Excuse me. So let's start with this notion with self-energy. And as usual, if you have questions, you just ask. So you remember that we saw that if we look at the propagator in a basis k prime, let's see, then I mean, this is the same as looking at the k 1 over omega plus I eta times the identity minus h, acting on k prime. And there is a Layman representation for this. We have discussed this. So all you need to do is to insert a complete set of states. Here, I did the Layman representation in the time representation, but you can do it in the frequency representation. So if the Layman representation then would look like this. So we would have the sum over energy eigenstates of let me anticipate a little bit what we will do. So sum over energy eigenstates of k n, and then here I have n K prime. And because these are energy eigenstates, I have omega plus I eta minus E n, because H has acted on these states. And so it has given me just E n, okay? So now these are just numbers. So now one thing I can do is this. I can do the integral d omega prime over 2 pi. And then I can put 2 pi delta of omega prime minus En. Okay, so I have done nothing, okay, because the 2 pi simplify and the delta function gives me 1. And now I can replace this by omega prime. Okay, so it looks as if I'm just going around in circles. But you see this, this is now like a spectral weight. We had chi-double prime before for response functions. Now we have what I will call A. So this is the integral d omega prime over 2 pi of A of k prime omega prime divided by omega plus I eta minus omega prime. Okay, so that's the spectral function. Now suppose I want to do just k equals k prime, and so in addition I will take k equals k prime, and in addition I assume that I have that k are good quantum numbers. Okay, so if k are good quantum numbers, it means that these eigenstates n here are momentum eigenstates. They are k. Okay, so basically I will have just one value coming out, the value for k equals k prime. So this will be equal to integral d omega prime over 2 pi times 2 pi delta of omega prime minus, let me call this epsilon k. Omega prime minus epsilon k divided by, I need to keep changing pen because they run out very quickly. So omega plus I eta minus omega prime. And I have a k prime. So you can think of this for now as just delta of k minus k prime. Okay. So what does it say? It says that the amplitude to stay in state k is just a delta function. Well, just a delta function. I mean, if I know the momentum k, I know the energy. Okay, this will be equal to k prime divided by omega plus I eta minus epsilon k. Okay, so let's consider this for always for k equals k prime. So we move always in the we just want to see the amplitude to stay in the momentum k. But now assume that k is not a conserved quantity. Okay, there are impurities or there are collisions, whatever. then what will happen to this spectral weight, the quantity in blue here? What will happen? So let me put A of k omega as a function of omega. If there are no interactions, I have a delta function. Okay, so if k is given, then there's only one energy. Okay. What will happen if k is not a conserved number? If k is not conserved, then it means that this will spread. Think of this in the following way. Go back to this formula. Take k prime equals k, and the energy eigenstates are not momentum eigenstates anymore. But the energy eigenstates will have projections, finite projections on momentum states k. If they are not too far, if we are looking at states that are not too far from the non-interacting states. Does it make sense? Okay. Now, what we know from the harmonic oscillator is not only that this broadens, but it shifts. Okay. So if the delta function was here at the beginning at epsilon k, then when k is no longer a good quantum number, this will be at some epsilon bar k. So let's see what happens if I write for the spectral weight here in blue. I write that A of k and omega. So I take just one momentum, the k prime, I take k prime equals k. Then if I take that this is 2 gamma divided by omega minus epsilon bar k square plus gamma squared. Okay, so I do something phenomenological. There's a width here, gamma, and there's a shift. Okay. So what happens now if I take this A of k and omega and I put it in this integral? You have done that in the homework. So this you can write as 1 over omega minus epsilon bar plus I gamma and minus I gamma. And then you can use the residue theorem, or you can use the residue theorem directly on this. So what will happen is that the answer, the Green's function, G retarded, I will call it G retarded of k and omega. Now this is not the operator, but that's really the expectation. G retarded of k omega will be equal to 1 over omega plus I eta minus I plus I gamma. Okay, and then, whoops, I'm missing the epsilon k. Minus epsilon bar k plus I gamma. So the I eta is not useful anymore, but we have the I gamma. So if I go in time now, G retarded of k and t is just the Fourier transform of this, and I get that is minus I theta of t, where theta is the Heaviside function, times the exponential of minus I epsilon, epsilon k bar t minus gamma t. Okay. So now what is the probability to stay in state K? Right, I know the amplitude to propagate from here to there. The probability is just the square of the amplitude. So I just need to take this times the complex conjugate. So it means that G retarded of K T square, so that's G times G star, is equal to E to the minus 2 gamma T. Okay? So I'm not staying in state K. I start in state K, but the probability decays. Okay? So that's the physical meaning of this, and even in the second quantized case, it would be the same result. Now, in the general case, we write that this is 1 over omega plus I eta minus epsilon k minus sigma retarded of k and omega. And this sigma is the self-energy. So here I took a very simple model where gamma was a constant and there was just a shift and so on. But the exact result can always be written this way, because you just take the inverse and then, this is just a definition of the self-energy. So in the present case, the self-energy sigma retarded of k and omega is equal to epsilon bar k minus epsilon k minus I gamma. But in the general case, that's what it would be. So the real part of the self-energy shifts the eigenvalue, the eigenenergies, and the imaginary part leads to a decay of the probability. So we will see later that this spectral weight can be measured directly with photoemission. And it can be interpreted as also as the probability of being in state K. Any question with this? Okay.
Excuse me.
Yes.
The theta t is normalized there.
Theta of t is just 1 or 0. It's the Heaviside function.
Okay. Gotcha. Thank you.
Yes, you forgot it in the last line.
Thank you. That's what you meant, huh, Surya? Yes. Yes, otherwise, when t is negative, it goes in the wrong direction. Okay, here you can write G0 retarded to the minus 1 of k and omega. That's a form we will see very often. Okay. So let us move to a second quantization. Any questions on this? So why do we call it second quantization? Do you know? Okay, what was the first quantization? And the first quantization, you take position and momentum, and you promote them to operators, and you act on wave functions. Okay. So you sort of start with particles, and you go to wave functions. But suppose now I want to quantize the electromagnetic field. Now I have a wave. Where are the particles? Okay. So that's called second quantization. You quantize the waves instead of the particles. So
So what you're saying is the first quantization is going from particles to waves, and the second one is going from waves to particles?
yes.
Okay.
And obviously it doesn't matter. I mean, one or the other is just as good. There's no single way of doing it. I mean, it's I will do it the pedestrian way. In other words, I will start from the particles and and introduce operators that will be second quantized operators. So the easiest way to think of it is the harmonic oscillator that you know very well. Okay. With the harmonic oscillator, you have position and momentum operators. And then you get the energy spectrum. And then you find out that you can go from one eigenstate to the other one by using ladder operators. Okay. And these operators are creation annihilation operators. Actually, I hope that the Canadian government is not listening to us today, because we may end up in the terrorist group, because we're talking about creation and annihilation. But we will do this on just on states, not on people. Okay. So so in other words, to go from one energy eigenstate to another one, you use these ladder operators, and they are like particles in a sense. You know, they go. You add one quantum of oscillation. So in that case, it would be bosons. But in here we will treat the case of fermions. So I will not discuss the case of bosons. It's done in the notes in chapter 24, and it's there are some subtleties associated with bosons, but it's not too complicated once you have the general idea. So why why boson and why fermions in the first place? Well, it's because particles are indistinguishable from the point of view of quantum mechanics. So if you interchange two particles, then you have to make sure that when you exchange them back, you get the same result. But the wave function is an object that's complex in general. So if you interchange two particles, and when you come back, you need to have the same result, there are two possibilities. You know, the one possibility is that the wave function changes sign, and then another minus sign gives you one. So that this fermions. And if there's no sign change, then it's boson. Okay. And they're very, so they're, in the end, it gives very, very different results. Now, if you're in two dimensions, it turns out that in interacting systems, there are other possibilities. So, because in two dimensions, you can tell whether you've been around a particle or not. But in three, so you can count these terms. In three dimensions, it doesn't make any sense, because you can go from here to, you can do like this, or you can do like this. It's all the same. So we will talk. So these particles that have different statistics than bosons and fermions are called anyons. So when they come out in the many-body case, but here we will just discuss fermions. So let me tell you just a couple of words about how to do it with it formally, and that's not what we're going to do. Okay. So the way it was proposed by Dirac to go from classical to quantum mechanics is to start from Lagrangians. And then the Lagrangian are functions of Q and Q dot. And there's a conjugate momentum. And then you postulate that these becomes that the P and Q become operators. And then the commutator of P with Q is equal to IH bar. And or if you want, this is what's obeyed with Poisson brackets. If you divide by IH bar, then these commutator become Poisson brackets. So a way to do second quantization is to use this recipe for the Scherlinger equation. So the Scherlinger equation, if you use this recipe for the Scherlinger equation, you will find that the quantity that's conjugate to the wave function. So you write the Lagrangian whose Euler equations of motion give you Scherlinger equation. And then you look for the variable that's conjugate to psi dot this way. And you find that this conjugate variable is IH bar psi dagger of R. So then you need to postulate that psi of R, psi dagger of R prime is equal to, so the IH bar simplifies because the conjugate is IH bar thing. So it's equal to delta of R minus R prime in the continuum. So, okay. Now let's not do it this way because anyway, what we will need is not commutator, which is for bosons, but anti-commutators. So by the way, at the end with the electromagnetic fields that are, there are complications associated with gauge invariance and so on, but basically what you do to quantize the electromagnetic field is just to look at the eigenmodes that are harmonic oscillators. So for each frequency k, you have a harmonic oscillator and you use the harmonic oscillator rule. Okay. So let's go to our pedestrian way of looking at things. Okay, so I start by looking at defining a basis. Alpha I, alpha J is delta Ij, okay? So you can think of alpha as, reminding me that I have a momentum basis or a position basis or whatever, or some localized states of some sort. And I equals 1, 2, 3 is just labeling these states, okay? So I assume that I have an orthogonal basis. Now, if I have two particles that are fermions, then it means that if I have alpha 1, alpha 2, one possibility is to write that this is alpha 1 tensor product with alpha 2. So what I mean here by tensor product is just that you have one Hilbert space here, another Hilbert space there, and they are next to each other. Okay? But why is this wrong? Because if I exchange alpha 1 and alpha 2, I don't get a minus sign. Okay? So I need to write 1 over square root of 2 alpha 1 cross alpha 2 minus alpha 2 cross alpha 1. Okay, and that's quite satisfactory here because I don't know which, let's say the Hilbert space is for particle 1 and one Hilbert space is for particle 1 and one Hilbert space is for particle 2. Excuse me. I cannot know which particle is in which state because they are indistinguishable. Okay. So particle 1 in that Hilbert space is at the same time in the states alpha 2 and in the state alpha 1. Okay. Now you see that it will become very cumbersome to generalize this to many particles. So what we prefer to do is to define creation operators. So creation operators. By the way, I think this was invented by Jordan, who turned out to be a Nazi, so that his name is sort of forgotten. So creation operators is the following. If I define an operator A that creates a particle in state alpha 1 acting on the vacuum, that gives me alpha 1. Okay. Now, the way these operators are defined is not only that they create out of the vacuum, whoa, dagger. Out of the vacuum, they create a state in alpha 1. They anti-symmetrize also. So suppose that I have A dagger alpha 1, A dagger alpha 2 acting on the vacuum. Then this is alpha 1, alpha 2. It is this state. Okay? So it means that these operators are defined in such a way that they anti-symmetrize this state. So because this has the property that it's equal to minus, let me put a minus very big, it's equal to minus alpha 2, alpha 1, then it means that these operators anti-commute. Okay? So this is equal to minus minus A dagger alpha 2, A dagger alpha 1 acting on the vacuum. Sorry, I don't need the minus here. That's the whole idea. I mean, the point is that if I put them in the reverse order, I get this. And this will be okay if when I add these two things, you know, if A dagger alpha 1, A dagger alpha 2 plus A dagger alpha 2, A dagger alpha 1 is equal to 0. In other words, this is equal to minus this. So we have a first result that we write this way. We define this bracket here as anti-commutator. So A dagger of alpha in state I times A dagger alpha J is equal to 0. Okay? Okay, now we need to define the conjugate with the adjoint, which is the destruction operator. They're also called annihilation operators. So either creation, annihilation usually is the more standard way of talking about this. We don't only destroy, we annihilate. It's even worse. Okay. So what do annihilation operators do? Well, if we take 0, A, alpha 1, this by definition is state alpha 1. Okay. So I'm taking the adjoint of this. I mean, this is a bra, so I'm taking the ket, which is the dual, but this operator now is the adjoint. Okay, so that's alpha 1. So now what happens if I take 0 times A alpha 1 0, and this is equal to alpha 1 0, and that is 0. Okay. Which means that I have found that the A alpha 1 acting on the vacuum is 0. So that annihilates the vacuum. That creates a particle, and that's on the vacuum, and that annihilates. Okay. Now, what happens if I take 0, A, alpha I, A dagger, alpha J, acting on 0. This will give me alpha I, alpha J. So this is equal to delta Ij. Okay. So what I do is now that I define, I will show you why I do this. I will write that the anti-commutator of A alpha I with A dagger alpha J is equal to delta Ij. Okay, that clearly works with this, because if I put this in the other order, then alpha A destroys the vacuum and it gives a 0. Okay, so if I bracket this commutator on the vacuum, it will give me delta Ij. But that's not sufficient, perhaps, to convince you. So the usefulness of this commutation relation, it is anti-commutation relation, is that it allows us to define the number operator. So what is the number operator? And everything we do, in some sense, will be based on the number operator. Okay. Now we are describing states. And I will show you next time that if we write operators like whatever operators you think of, if we write operators using these creation annihilation operators, then it becomes very easy to manipulate these expectation values. It would be very complicated in first quantization because we would need to work with determinants, as I will show you when we look at the wave function. I won't have time to do it today, but you will see that it's a clear simplification. Okay, so what about the number operator? Well, anyway, I won't have time to use all this space now. But let me make a little bit of space. Okay. So I define the number operator n alpha as a dagger alpha, a alpha. And all that the operator does is to count the number of particles in state alpha. Okay, to show you this, let's act with the n alpha on the state 0. Okay, so that gives 0. Okay, because A acting on 0 is 0. So then alpha has discovered that there are no particles in state alpha in that state. Now, if I take at n alpha on the state A dagger, oh my God, so these pens are really getting a pain. So A dagger alpha 0. Okay. Then I write that this is A dagger alpha A alpha, A dagger alpha acting on 0. Okay, that's the same. Now let me use the anti-commutation relation that is here. So this is A dagger alpha times 1 minus A dagger alpha, A alpha acting on 0. And now A alpha acting on 0 is 0. Okay, so that's A dagger alpha 0. So you see, I get the same state with eigenvalue 1. So I have discovered that there's only one particle in state alpha. Okay. Now suppose that I want to look at n alpha on a state, a more complicated state, which that is, let's look at A alpha I. So the A dagger alpha 1, A dagger alpha 2, and then I have some A dagger alpha I, and then I have some other A daggers alpha n acting on 0. Okay, so I've created a many-body state. Now you see that oh, I forgot to write this important relation here. If I look at this is the number operator again, okay? This piece here. So it means that here I have shown that, let's say the important relation, I've shown that n alpha with commutator this time with A dagger is equal to A dagger. Okay. But now if these labels are different, I, J, then I get A dagger alpha J, but only if I is equal to J. Otherwise, I get 0. Why is that? Well, it's because if if I have A dagger alpha I, A alpha I, and I have A dagger alpha J, then these anti-commute, and then these anti-commute as well, because I and J are different. So it means that this piece here is commuting with this piece. Okay? So if I and J are different, then it commutes. So, okay, getting back to this. Now N alpha I, okay, commutes with all of these. Then when you get to this, you can just commute it. You can use this relation, and you can leave A dagger behind, and you have okay, this is equal to the same the same state. So M A dagger alpha alpha is equal to A dagger alpha plus A dagger alpha N alpha. Okay. So when this acts on this the same with the same label, you leave this. So this state is the same. And then you have plus the state where now N is to the right. Okay. Now when N is to the right, you can commute it through all the other operators and kill it in the vacuum. Okay. So it means that if there is one particle, you get the eigenvalue 1. And if this particle is not there, then you get 0. Okay. And by the way, I mean, it was clear from the beginning, but this formalism contains the exclusion principle. Why? Because if I have A dagger alpha, A dagger alpha acting on 0, these things anti-commute. So it's equal to minus A dagger alpha acting on 0. So an operator that's equal to minus itself is 0. Okay? So you cannot create two particles in the same state. So that's the exclusion, the Pauli exclusion principle. Okay, so this will be very important. We will use this operator a lot next time. The other important things are the change of basis and the wave function. So I will do that, and I will do the show you operators next time. But let me finish with one comment and two comments. In fact. One is that you see that this formalism is sort of a nice way to think about wave-particle duality. Okay, because whatever the state I'm looking at, I always have 1, 2, 3, 4, 5. I have particles all the time. And they come in bunches. I mean, there's one particle, there are two particles. There's not, okay. If you look at probabilities of having particle in a state, then that cannot be equal to 1. That it's possible, I'm sorry, it's possible that it's not equal to 1. But if you count particles, you always get a number. Okay. And then in what state these particles are, well, You know, they can be in a plane wave, for example, or they can be in a position state, or in one orbital in an atom, or it could be that you have a linear combination of these n particles all in plane waves, plus these n particles all in orbitals. Okay, so you see, it can be arbitrarily complicated. Okay, and my last comment, so I won't let you suffer all this erasing. So my last comment is this. Suppose now that I want to exchange I have this state here, okay? And I want to exchange these two particles. I should also get a -1. But there are a bunch of particles here in between. Does that work out? We need to see if the formalism is consistent, because the way we fill particles here is completely arbitrary. We just have to, we make a choice. It's a choice of basis. We fill these in a certain order, and then we do calculations with them. So let's suppose we have chosen some order. When we permute these two things, we need to get a -1. So let's see if it works out. Here, I will anti-commute this creation operators with all these other ones here in between, okay? And every time I get a -1 because of this. So every time I get a -1, so I will get -1 n times. And then now these two operators are next to each other, okay? I propagated here, and they are next to each other. Now I anti-commute these, so that gives me another minus sign. So I get +1. And now this guy, which is that is now to the left of this one, I can anti-commute it back to where this one was. So that gives me another -1 to the n. So overall, I just have 1 -1. Okay? So the formalism works out in a very simple way. Okay, so next time we look at the change of basis. That's very, very, very important idea. And we will look at the momentum and position basis that we will use repeatedly. And I will show you that the wave function in first quantization is a determinant that's called the Slater determinant, and write the operators in second quantization, and we're all set with second quantization. Okay, not much mystery. Okay, any questions? Okay, so see you Monday then. And if you want, I'm staying. If you have some questions, I'm staying. Okay.